Your brain is the single most energy-demanding organ in your body. Despite its size, it burns through 20% of all the energy you consume. Inside your skull, roughly 86 billion neurons are firing in coordinated patterns. Each individual neuron can form connections with up to 10,000 others, creating a staggeringly complex web of approximately 100 trillion synapses. This diagram compares the energy budgets of your internal organs. To keep this specific network alive and responsive, your body spends somewhere between 400 and 500 calories per day, roughly 1,600 to 2,100 kilojoules. The vast majority of that energy arrives as glucose molecules, simple sugar. For nearly every person, this is the dominant fuel source powering every thought and memory. In this schematic, we see glucose molecules crossing the blood-brain barrier. They enter through specialized transport channels known as glucose transporter type 1, or GLUT1. Your entire conscious experience, everything that makes you feel like you, is currently powered by these molecules being broken down for energy inside your neurons. But a growing number of neuroscientists are now investigating the long-term cost of this dependency. They are asking if relying exclusively on glucose is what actually wears the brain down. Every time your neurons metabolize glucose for energy, they produce metabolic byproducts. One of the most damaging categories is reactive oxygen species. Think of them as tiny sparks flying off an overworked engine. One spark is harmless, but billions of them, generated every hour for decades, cause physical damage. These particles chip away at the delicate membranes surrounding your neurons. They damage the genetic material coiled inside your brain cells and trigger a slow, persistent state of inflammation in neural tissue. Over time, this invisible damage accumulates into recognizable symptoms: brain fog, difficulty concentrating on simple tasks, or forgetting a word that was on the tip of your tongue just seconds ago. While many assume these are just signs of aging, research suggests they may be symptoms of the collateral damage left behind by your brain's primary fuel source. It is possible to transition the brain to a fuel source that generates more energy with fewer byproducts. This data shows the metabolic shift. When carbohydrate intake is restricted to roughly 20 to 50 grams per day, the liver begins converting stored fatty acids into molecules called ketone bodies. The most important of these molecules is Beta-Hydroxybutyrate, or BHB. This chart tracks BHB levels as they climb in the blood and travel toward the brain. Research published in the Journal of Cerebral Blood Flow and Metabolism suggests that BHB generates more ATP, or cellular energy, per molecule than glucose. Simultaneously, this process produces fewer reactive oxygen species. It appears to be a more efficient fuel for neural tissue. In metabolic terms, this is like replacing a smoky coal furnace with a modern, high-efficiency power system. You get more energy output with less toxic waste. The ketogenic diet originated nearly a century ago, long before it was associated with modern weight loss or fitness trends. It was developed by a physician at a major medical institution for a specific clinical purpose. The original reason this protocol exists was to rescue a feiwan brain. That chapter of medical history has been largely buried by social media trends, but it holds the key to what this metabolic state actually does to the mind. However, the transition is difficult. During the first 72 hours of carbohydrate withdrawal, the brain essentially panics. Without its usual fuel, it triggers a period of severe symptoms. Before reaching a state where your neurons are protected from long-term decline, your brain must first endure a brutal, panicked withdrawal from its primary energy source. Hour 1 begins the moment your last significant serving of carbohydrates is digested and absorbed. At first, your brain continues to burn glucose normally, pulling from the steady supply circulating in your bloodstream. Your body maintains a specific reserve for this energy. An average adult carries roughly 400 grams, about 14 ounces, of glycogen in the liver alone. This stockpile serves as the brain's emergency fuel. When you slash carbohydrate intake to nearly zero, this reserve drains like a bathtub with the plug pulled. While nothing feels different on the surface, your body has officially started a biological countdown toward systemic starvation. 12 hours in, blood glucose levels dip. While the levels remain within a safe range, the drop is enough for your hypothalamus, the brain's energy monitor, to notice the deficit. To the brain, falling blood sugar signals that you have failed to find food and may be in the presence of predators. It interprets the lack of glucose as the beginning of a famine. The hypothalamus reacts by releasing cortisol and norepinephrine. These chemicals place your entire nervous system on high alert, preparing the body for a state of emergency. By the 24-hour mark, you begin to feel the keto flu. Headaches settle behind the eyes, irritability flares without warning, and concentration becomes heavy and sluggish. Imagine your brain as a city powered by a single electrical grid, glucose. As you restrict carbohydrates, you are effectively switching off that grid one district at a time. The lights flicker and circuits misfire, creating noise and confusion within the system. Your brain is currently caught between two systems. The old glucose grid is shutting down, but the new power source is not yet fully online. This cognitive heaviness represents a physical withdrawal. Your brain has spent a lifetime dependent on a steady stream of glucose, and that stream is running dry. As glycogen reserves vanish and blood glucose continues to fall, your liver receives the signal to act. It initiates ketogenesis, a process where stored body fat is broken down into fatty acids. Through a series of enzymatic reactions, the liver converts those acids into three distinct types of ketone bodies. The most important of these for your brain is BHB. Within 48 to 72 hours of carbohydrate restriction, BHB begins appearing in the bloodstream. It typically reaches concentrations of 0.5 to 1.0 millimoles per liter, crossing the threshold into a viable fuel source. This chemical manufacturing in the liver provides the essential energy needed to sustain the brain while the primary glucose supply is restricted. As BHB levels rise, the blood-brain barrier begins a physical remodeling. The brain constructs new entry points to allow this alternative fuel inside. These new doors are a transporter called MCT1. The brain upregulates these transporters, creating pathways that previously did not exist in significant numbers. Because this biological construction takes days, you experience a temporary cognitive dip. You feel foggy and sluggish while the old system fades and the new ketone system is still being built. By the end of day 3, the fog begins to thin and the mental static dissolves. The world feels sharper and conversations become easier to follow. This sharpening of the senses marks the moment your brain successfully metabolizes its first significant quantities of BHB for energy. The BHB molecules enter your neurons and feed directly into the mitochondria, the tiny power plants inside every cell. Ketone metabolism within these mitochondria triggers a shift in the brain's production of neurotransmitters. This process reduces levels of glutamate, the brain's primary excitatory neurotransmitter, the neural gas pedal. Simultaneously, the brain increases production of GABA, your primary calming signal. The balance shifts, the brake gets stronger, and the gas pedal eases off. By the first week, your brain reaches a dual fuel state. Ketones now account for 60% of its energy budget. The remaining 40% is supplied by glucose that your liver manufactures from non-carbohydrate sources through a process called gluconeogenesis. This 1-week milestone represents only the first phase of adaptation. Over the next 3 weeks, these cellular transformations deepen, leading researchers to investigate whether this metabolic switch can effectively mitigate depression and age-related cognitive decline. By day 7, your brain crosses a physical threshold. The initial withdrawal fades, the keto flu breaks, and as we see here, Beta-Hydroxybutyrate is now flowing steadily across your blood-brain barrier, using newly constructed MCT1 transporters to deliver cleaner fuel directly to your neurons. This shift in fuel marks the beginning of a window between day 7 and day 30, where the brain begins to restructure its internal environment. Research indicates that the presence of these ketone bodies triggers the brain to increase its production of brain-derived neurotrophic factor, or BDNF. This protein is the primary architect of neural repair, dictating whether your neurons survive and maintain their structural integrity. Neuroscientists often describe BDNF as miracle grow for the brain. It keeps existing neural pathways resilient while actively promoting the growth of new synaptic connections, the literal foundation of how you learn and store memories. As we age, BDNF production naturally drops. We see similar declines in people experiencing chronic anxiety, depression, and neurodegenerative conditions. The infrastructure begins to degrade. By maintaining a ketogenic state for 30 days, you are forcing the brain to invest in its own hardware. It repaves the old roads and reinforces the aging bridges, physically expanding your capacity to process and retain information. But BDNF is only the outer layer. If we zoom past the synapses and look deep inside a single neuron, we find hundreds to thousands of mitochondria. When your brain runs primarily on glucose, these power plants accumulate damage over time from reactive oxygen species, a highly reactive byproduct of standard cellular metabolism. Ketones activate a master regulator protein called PGC1-alpha, triggering mitochondrial biogenesis. Neurons begin demolishing aging factories and constructing fresh, clean energy facilities. By weeks 3 and 4, a graph overlay shows measurable increases in mitochondrial density and ATP production inside the cells. More density means more ATP. Your brain secures a steady stream of power that eliminates the severe afternoon crashes tied to high carbohydrate diets. Outside the neuron, the brain maintains its own specialized immune force. These are the microglia, and they patrol your neural tissue to clear out debris and neutralize threats. But years of metabolic stress from excess glucose and insulin can force these microglia into a state of chronic activation. They begin releasing inflammatory signaling molecules called cytokines, damaging the exact neurons they are designed to protect. BHB acts as a targeted inhibitor, physically binding to the NLRP3 inflammasome. The cytokine cascade halts, and microglia return to their normal surveillance state. By day 30, this cooling mechanism measurably drops systemic markers of inflammation, including C-reactive protein, extinguishing the fire. When you combine these three biological pillars, the surge in BDNF, the construction of fresh mitochondria, and the silencing of chronic neuroinflammation, you arrive at a very specific psychological state. People usually call it mental clarity. The background noise of the brain goes quiet. Decisions require less friction, focus becomes effortless, and you maintain a steady energy from morning until night. Have you ever hit that exact state of effortless focus where everything just clicks? Let us know what that felt like for you down in the comments. This feeling of clarity has a direct cellular basis. It is the result of your neurons operating within an optimized environment at peak capacity. But before you swap every meal for a high-fat alternative, we have to look at the other side of the ledger. The ketogenic diet carries real, sometimes dangerous side effects if mismanaged. There are specific groups of people who should never attempt this extreme metabolic shift without strict, ongoing medical supervision. To understand why, we have to open a forgotten medical file from the 1920s. A doctor was desperately searching for a treatment for an entirely different ailment. At the center of his research was a specific group of children facing a medical mystery that the establishment could not solve. Uncovering the true story of how this protocol was invented provides the final piece of the puzzle, revealing what it was always designed to do. 30 days of nutritional ketosis produces documented changes in how your brain functions, but achieving that state is not a simple upward trajectory. Transitioning your body's primary fuel source carries substantial, immediate physical risks. The initial danger begins with a very specific biological trigger. When you drastically reduce your carbohydrate intake, your insulin levels plummet. That drop signals your kidneys to begin excreting unusually high amounts of sodium. And in the human body, where sodium goes, water follows. In the first week alone, most individuals lose between 1.4 and 3.2 kilograms, primarily in rapid fluid loss. That rushing water strips the body of essential electrolytes, pulling down levels of sodium, potassium, and magnesium. That sudden mineral drain causes immediate physical consequences. A sudden drop in magnesium often leads to heart palpitations and persistent sleep disruption. When potassium levels fall too low, the body struggles to maintain proper nerve signaling. Failing to strictly manage this severe mineral loss directly interferes with the way your neurotransmitters communicate. Without those essential electrolytes, the transition deepens the exact brain fog the individual was trying to cure. The risks extend outward to the cardiovascular system. Sustaining a high-fat diet causes a notable increase in low-density lipoprotein, or LDL cholesterol, in some individuals. This requires active, professional medical monitoring. There is also a critical, life-saving distinction between nutritional ketosis and diabetic ketoacidosis. For individuals with type 1 diabetes, pushing the body to generate ketones carries a severe risk. If ketone concentrations rise to dangerously high, unmanageable levels, the blood becomes toxic. Certain biological profiles face inherent dangers from the high-fat requirements of this diet. People who have had their gallbladder removed, individuals with inherited fat metabolism disorders, and pregnant or breastfeeding women lack the biological capacity to safely process this nutritional load. Anyone currently taking medication for a neurological or psychiatric condition must consult a physician before attempting this transition. Ketone bodies alter neurotransmitter levels, and they can interact unpredictably with those specific medications. The potential brain benefits of nutritional ketosis must always be weighed against the broader metabolic picture. No single organ exists in isolation from the rest of the body. To understand why this diet affects the brain so powerfully, we must travel back to the Mayo Clinic in 1921. Dr. Russell Wilder was struggling to treat severe, drug-resistant epilepsy decades before modern anti-seizure medications existed. Physicians stretching back to ancient Greece had recorded a strange medical observation. When patients completely fasted for extended periods, their violent seizures often decreased dramatically or stopped altogether. The dilemma was obvious. Extended starvation mimics a cure, but it eventually becomes fatal. Dr. Wilder needed a biological workaround, a way to replicate the precise metabolic state of fasting without starving his patients to death. His solution was extreme engineering. He designed a diet heavily loaded with fat, containing moderate protein and completely devoid of carbohydrates, the exact nutritional profile required to force the continuous generation of ketones. The clinical results were staggering. Children suffering from severe epilepsy saw a 50% or greater reduction in their seizures. For the first time in their lives, some of those children became completely seizure-free. Dr. Wilder's ketogenic diet was engineered a century ago to mimic the metabolic effects of starvation and halt violent electrical storms inside the human brain. The foundation of this success is direct stabilization. Ketosis calms the chaotic electrical activity of individual neurons, forcing them back into a steady rhythm. This data model shows the internal chemistry behind that calm. Ketosis shifts the balance between neurotransmitters GABA and glutamate, heavily toward GABA. Ketones also provide a cleaner energy source, generating fewer reactive byproducts, decreasing neuroinflammation, and stimulating the renewal of mitochondria. The precise mechanisms that stopped epileptic seizures 100 years ago are the exact biological pathways modern researchers are now exploring to treat depression, anxiety, and age-related cognitive decline. For a 30-day cognitive experiment, the clinical data establishes a strict macronutrient rule. You have to keep your net daily carbohydrates tightly between 20 and 50 grams, roughly 0.7 to 1.8 ounces. Your fuel source matters just as much as the limits. The framework requires prioritizing whole food fats, relying on extra virgin olive oil, nuts, seeds, and fatty fish, rather than highly processed alternatives. Daily electrolyte management is a non-negotiable requirement. Adequate intake of sodium, potassium, and magnesium must be maintained consistently across the entire 30-day window to prevent neurological disruption. The biological timeline requires strict discipline. While the initial transition takes 3 to 7 days, achieving full neurological adaptation, the point where the brain efficiently runs on ketones, requires 3 to 4 weeks of unbroken carbohydrate restriction. Achieving mental clarity through ketosis requires a month-long commitment to rewiring your body's entire energy infrastructure. But human biology is fiercely individual. A fuel switch that produces profound mental focus and high energy for one person might cause persistent mood disturbances and deep fatigue in another. That response is dictated by invisible factors: your baseline metabolic health, your genetics, your sleep quality, daily stress levels, and the specific bacteria in your gut microbiome all decide how your brain reacts to ketones. This is an educational framework based on historical and current science, not medical advice. Dramatic changes to your health routine require direct consultation with a qualified clinician. The history and science of nutritional ketosis offer a verified tool for cognitive intervention, but when dealing with the unique biology of the human brain, there are no universal guarantees.